Hi, this is Physics, Chapter 13, Part 2 for kinetic theory. Sorry. We left off with gas laws. We're going to start looking at Boyle's law and Charles' law and Gay-Lussac's law. And each of these stems from what we call the ideal gas law, and kind of all build to that ideal gas law. And you can always kind of use the ideal gas law in a sense if you know certain things, but what these do is, assuming certain things aren't changing, it kind of boils down this equation, so you have different relationships. So one thing I want to mention with this is the amount of gas is not changing right now. I guess I don't need that E. Changing. And that means that the number of moles is the same. Okay. That's important. Let me bring up the ideal gas law so you know why I'm mentioning that. So ideal gas law is PV equals nRT. There's also another form which we'll get into, but I'm not going to use this one just because it has the number of moles. This R is already a constant. It never changes. Right, so that's a constant. This is the number of moles. Okay. This is temperature. This is pressure. And this is volume. So we're going to say in this first one with Boyle's law is that we're at constant temperature. Okay, in some way we are holding this temperature constant. And so what we have changing is the pressure and the volume. And so let's say we have an initial state here. I'll call it 1. Pressure in the original state 1, volume in that original state 1. And it's going to equal N R, which is a certain amount of gas, all constant, and the temperature. And we can call it temperature in state 1, but remember we aren't changing the temperature, so I'm just going to have that as just T. Right. Now if we change this gas without allowing anything on here to change, we'll have a pressure 2 and volume 2. And it's going to equal same number of moles, because that hasn't changed. Same gas constant, because that won't ever change. And we did it at the same temperature. And so we get P1 V1 is equal to nRT, as well as P2 V2 is equal to nRT. So P1 V1 equals P2 V2. And this is Boyle's law. Okay, and it equals some constant, which is nRT, depending on the number of moles, depending on the temperature. But if you have these different states, you don't even need to know this stuff because you can calculate it from here. So you can see we have a graph, pressure on the y-axis, V on the volume axis. As pressure is high, you will have a lower V. And as the pressure decreases, the volume increases. And once you get a high volume, you will then have a lower pressure. And that's because these are inversely proportional. Okay, when one increases, the other one has to decrease in order for this to stay constant. Okay, think about this as if I have pressure as 3, volume as 4, and I'm not even going to worry about units right now, and this nRT equals 12. Well, if this goes up to 6, and this has to stay constant, then that has to go down to 2. And that's how it's inversely proportional. So one increases, the other has to decrease. We can think of this as with an application. You have this piston here. Okay, at this point, this initial point, you have a very small volume. And inside here, you got all these molecules, the volume's small, they don't have much space, so you'll end up with higher pressure as they start hitting the walls and bouncing off of each other and are feeling more claustrophobic because of the pressure inside. If you expand that volume and you change that volume and you increase that volume, it reduces the pressure inside because now they have more room, they can move around more, they're not as claustrophobic. And this is assuming you do this with the temperature not changing. Right, so if we have a gas sample has a volume of 150 milliliters, when the pressure is 175 kPa, the temperature amount of gas remains constant, what volume will the gas sample occupy at a pressure of 120 kPa? So P1, V1. P1 is 175 kPa. V1 is 150 milliliters. And then they tell us the pressure 2 is 120 kPa. Now, with units, all we care about is that these are the same. And then this milliliter then will give us the milliliters of volume 2. So when we calculate this, that's what we're going to end up with, is milliliters. So pressure 1 is 175 times volume 1 is 150 equals pressure 2, which is 120, times volume 2. So 175 times 150. Where's my calculator? Oh, yeah, it's this little thing. 150 times 175. That's going to be 26,250 equals 120 V2. And so we divide this by 120, and we get our answer. And you get 218.75. Now be milliliters. Alright, so when we decrease the pressure, that means we had to have the volume increase. Alright. The next law is Charles' law. I don't really expect you to know the names of these, just kind of when it says constant pressure, constant temperature, what equations we're looking at. That's, oh, alright, thought I drew this. That's usually a little bit easier to remember. Charles' law is constant pressure. Okay, and one way to memorize these equations is to memorize this one. Okay, constant pressure meaning this stays constant. Okay, so now I have this memorized. Well, V and T are on opposite sides of the equation. So if I want all the constants on one side, I have to divide P over. So I get NR over P. And I gotta divide T over, so I get V over T. Okay, so now I have this one memorized. V1 over T1 equals V2 over T2 equaling some constant, which will be technically NR over P. And depending on what the moles is, at what pressure you are, will depend on what constant that is. Alright, so The idea with this is you have another piston here. This one you have a volume inside, but you're going to force this pressure stay the same. And so you start to heat this up. So you add more heat. The pressure is the same, so the volume has to increase out. And so as the volume increases out with temperature heating, you end up with a new volume for a new temperature, and an increased volume with an increased temperature. So another way to remember this is as the volume increases or the temperature increases, the other one will also increase. So increased volume, increased temperature. Decreased temperature, decreased volume. It's a linear proportion. So if we were to measure these different volumes and temperatures, it's going to fall on this type of graph as you move up. I did not mean to do that. Okay, whoops. Sorry about that. It's going to move up. Oh, come on. I keep hitting off to the side. I keep hitting that. Okay, it's going to move up. And it's going to all be linear. If we trace this past down as far as we can go, no matter what element we're dealing with, it all arrives at the same spot. And that is what we have deemed absolute zero, which is a negative 273.15 degrees Celsius. Alright, so let's look at an example here. A 650 milliliter, so that's volume 1, of gas is collected at room temperature, that is 30 degrees Celsius. So that's going to be temperature 1. What volume will the sample be at 0 degrees Celsius? So temperature 2. And now I'm going to do something very bad. I'm just going to plug these in real quick. So 650 over 30 degrees Celsius equals V2, which is what we want to find, over 0 degrees Celsius. Well, this is what I was talking about. This is the problem. We can't divide this. And so because we can't divide this, we're setting a whole problem up where it's kind of not allowed. We have to switch these to Kelvin. Okay, remember from our equation, let me go back up to it in case you don't remember. K equals C plus 273. We have C, we want K, so that's the equation we want. K equals C plus 273. Alright, so we can say we know the temperature here is 273, that's 0 plus 273, and 30 plus 273 is 303. And so we can rewrite this 650 over 303 equals V2 over 273. So V2 equals 273 times 650 over 303. Which is 585.6. This is milliliters. Okay. Notice if we would not have done that and we would have just kept this and multiplied 0 over, well, now you got 0 multiplying everything. And so that makes that whole thing 0, and you get your volume 2 equaling 0 degrees Celsius, which is 273 Kelvin, which is I'm sorry, that's not Celsius. You get your volume equaling 0 milliliters. Got a little caught up with that being 0. So volume is 0 milliliters, not the same as the volume here. And so this one's wrong because we cannot do that. And so we have to switch them to Kelvin. Right, so the Gay-Luxic is done at constant volume. And the idea is very similar to one we just did. Okay, P1 over T1 equals P2 over T2. Again, temperatures gotta be in Kelvin. It means the pressure and temperature is proportional, which we can see that these are on the opposite side of this equation. And so you have this linear change to it. So as pressure increases, so does temperature. Pressure decreases, so does temperature, and vice versa. Alright, so, and let me just kind of solve this for P over T. Right, so this constant is going to be your N R over V. So it depends on the volume you're dealing with and the number of moles. But when you're keeping that constant and all this constant, we can look at the relationship just in this way. Alright, so we have an aerosol can of hairspray. It's filled to a pressure of 50 psi. And our room temperature is 25 degrees Celsius. So that's going to be, add 273, you get 298. Kelvin. And we want to calculate the pressure inside the can if the can is placed in boiling water. And I guess we're going to assume that it comes up to equilibrium. So temperature 2 is going to be 100 degrees Celsius. So it'll be 373 Kelvin. Alright, so we can set the equation. P1 is 50. T1 is 298. It's going to equal P2 over 373. So we multiply 373 over. We have P2. So P2 equals 373 times 50 divided by 298. And you get 62.6. And we're looking at pressure. PSIs is what we had, so PSIs is the unit we have. Right, so that's the third law. Right, all of these work with just holding one of them constant and seeing how the other two, pressure versus volume or pressure versus temperature or volume versus temperature, how they change with one another. Right, so now let's actually get into this ideal gas law. And this, a lot of times, this would be used when you don't have one of those three being held constant, but you still have states of the gas changing. Right, and so we're going to start with first this PV equals nRT. And we're going to start with looking first at what this N is. N is the number of moles of a gas and is equal to the mass over the molecular mass. Okay, so let me make sure I have a periodic table coming up. I guess I don't. Alright, so you know what? Let me get a periodic table so I can show you guys. I thought I had one coming up in the notes, but I guess I don't. The easiest way is just Google periodic table, find a decent one. Alright, so let me see when I can click on and get it bigger. So I see one that has the numbers on the bottom as well. That one doesn't. This one does, okay. So we're looking at chloride, which is CO2. So we have two of these. And chloride's molar mass is 35.45. So we're going to round that to 35.5. Okay, I'll keep this up. Just minimize it. So for chloride, which is Cl2, you have a molar mass equals 35.5 times 2, right, which would be 71. And this would be, we go to the beginning of our chapter. I'll show you where we have it listed. I list the units. This is grams per mole, okay? And that's important. That's one thing it means that we have to have a mass in grams. It's one of the few times we have a mass in grams, but it's necessary. Alright, so this is grams per mole. And so if we want to calculate our number of moles, if we have 30 grams, that's our mass. We have 71 grams per mole. That mole is going to go to the top, so we're going to end up with moles as your unit. Grams cancel. 30 divided by 71. 0.42. Right, so this is the number of moles. And that's how you would calculate it for anything. If we had anything that's something more complicated, well, NH3. Okay, we're gonna have one N, which we can get here in a minute, and we're gonna have three H's. So the N is gonna be 14 grams per mole. It's like 14.006, so 14, and the H. Let me see if this pops up so I can see the H. H is 1.00. No, it's hard to see. Yeah, this is 1.007. So 1 and 14 are molar masses for these. So 1, so 3 times 1, and 14. And so we'll add these together, we end up with 17 as our molar mass. So 17 grams per mole. And then we would use that depending on how much mass we actually have of the gas to find out how many moles. Alright, so The next part of this is, since we looked at the N, now we haven't looked at the R yet. That has actually two numbers. I said it was both constants. These are technically the same, but the units are different. This 8.31 is joules per moles Kelvin. And the moles Kelvin, that deals with the N and the T. It's the P and the V that depend on one another. And so this one will depend on a pressure that is in pascals or newtons per meter squared, since they are technically the same. And then the volume is in meters cubed, or something we can get into meters cubed. Like, I mean, we can get anything into meters cubed, but like centimeters cubed, we can easily convert that to this. When R is 0.0821, we have liters and ATM. Okay, so volume would be in liters, and pressure is in ATM. Okay, so if we have a pressure in torr or millimeter mercury, we have to convert it to one of these. If we have a pressure in one of these, we have to make sure the volume matches up. We can't use liters over here or meters cubed over here. The numbers just won't match up. And that decides which one of these we use. Let me check the time. Okay. Right, so if you collect a volume, 1.75 liters of hydrogen gas during a lab experiment, and the room temperature is 23 degrees Celsius, and the pressure is 105 kilopascal. How many moles of hydrogen will you have? So we want to know N. Okay. We also need to figure out what R is. And that's going to be the first thing to figure out, is what is R. Alright, so we want to look at this, and we said, okay, well, if pressure was pascals or newtons per meter squared, we use the 8.314. Right, so we do 8.314, but we also know we have to convert this to pascals. It's in kilopascals. That's an easy conversion. 1 kilopascal is 1,000 pascals. So we'll be multiplying this by 1,000 to get 105,000 pascals. Right. At this point now, we have to come up here to liters. And we're going to have to, liters doesn't match up with the pascals. The liters is over here. So we're going to have to convert this to meters cubed. And I don't remember the conversion directly from liters to meters cubed. What I do remember is this. 1 liter is 1,000 milliliters. 1 milliliter is 1 centimeter, or a centiliter, I guess you can call it. No, that was right. 1 centimeter cubed. And then 1 centimeter, or I should say 100 centimeters cubed. So 100 cubed centimeters cubed is 1 meter cubed. Right, so we're going to multiply by 1,000, divide by 100 cubed. I get 0. Well, hold on, let me do it on the other calculator so you can see. Right, so 1.75 times 1,000. That's converted to milliliters. Divided by 100 cubed. You get 0.00175. And that's how many moles. Okay. Now we could have taken this, converted this actually to ATM, and used the other R constant. And that's actually how I did my notes. But I kind of jumped the gun here, and so that's why I had to convert it this way. Wait, I'm sorry. That's not N. I jumped the gun on that. That's your volume. We haven't figured out N yet. Okay. So now let's figure out N. Okay, so we have PV equals NRT. P is 105,000. V is 0.00175. N is what we're solving for. R is 8.314. And temperature, we gotta convert this Kelvin. So add 273, you get 296 Kelvin. Right. The reason we have to convert this temperature is because we're going to be dividing over. And whenever you're dividing a temperature, you cannot have it be even possible that 0 could be in it. So we get N equals 105,000 times 0.00175, 8.314 times 296. Right. Now the rule of thumb is if you just see a T in the formula, not a delta T, use Kelvin. Let me go to my other calculator. Keep forgetting that. Oops, scroll down on that by accident. Right, so 105,000 times 0.007175. Okay, divided by 8.314 and divided by 296. And we get 0.075. 0.075 moles. There we go. Right. As I said before, we could have done this where we changed that volume. So let's say we have 175 liters. T is 296 still. If we use the other R, which, let me scroll back up to it, the 0.0821, that's liters in ATM, so we gotta switch this pascals from 105 kilopascal times 1 ATM over 101.3 kilopascals. And you get 1.04 ATM. And then when we plug this in, PV equals nRT. P is 1.04 times 1.75 equals N times 0.0821 times 296. And so if I plug that into a calculator, so 1.04 times 1.75 divided by 0.0821 and then divided by 296, and you get the exact same 0.075. And so basically you got different ways of doing this. You just have to pick which one's quicker. I would have done it normally this way. I kind of started with that, and it kind of set me having to do it this way. All right. Now, check the time. You know what? I'm going to stop the video here, so it won't be as long, and I'll do a third video. I should probably be able to finish up everything in the third video. We're going to start again with the ideal gas law, but this is a new way of doing it, and we see that they are related with this way, but it deals with number of molecules and another constant instead. And then I'm going to start looking at how you know which way to go. Right, and so that's where I'm going to start the third and should be the final video in Kinetic theory. Right, I'll see you in the next video.